Alright, let's look at example 1. Solve the given differential equation by variation of parameters. Alright, so we're going to go ahead and solve this differential equation, the second order, and it's set equal to tangent of x. So we cannot use undetermined coefficient. So now we have y double prime plus y. So the first thing we're going to do is we're going to set y double prime plus y equal to 0 to find the homogeneous, to find the particular solutions. Now, we're going to go ahead and change y double prime plus y to m squared plus 1 equals 0. And we're going to go ahead and solve for m, and we're going to get m is equal to plus or minus I. So that means that our alpha is equal to 0 and our beta is equal to 1. If you recall, right, and again, it's been a while, the solution for, when you're equal to a complex, when m is equal to a complex number, then y is equal to e to the alpha x times c sub 1 beta x plus c sub 2 beta x. Well, if alpha is 0, then we'll substitute that in there, and beta is 1, then we're just going to go ahead and substitute those in. Then our y sub c is going to be c sub 1 cosine x plus c sub 2 sine of x. So we were able to find our complementary solution pretty quickly. Now we want to find our particular solution. So from y sub c, you should be able to find your y sub 1 and your y sub 2. That's where y sub 1 and y sub 2 are going to come from. And so here we have our y sub 1 and y sub 2. So we have those written there. Now, we want to go ahead and use our Wronski. So we're going to go ahead and look at this, look at our function and see what it's set equal to. So we know that our what I should have done is written this. Actually, I'm going to write this down now. Over here to the right is that we know that it's going to be u sub 1 prime times y sub 1 plus u sub 2 prime times y sub 2, and then u sub 1 prime times y sub 1 prime plus u sub 2 prime times y sub 2 prime, and that equals 0, and that equals our function. So using this, our y sub 1 is going to be, actually I'll just write that out here. So then our u sub 1 prime is going to be cosine x plus our u sub 2 prime times y sub 2, which is sine of x, equals 0. And then we can say u sub 1 prime times the derivative of cosine is going to be negative sine plus u sub 2 prime times cosine x equals tangent x. Just in case you're ever worried about where we're getting our numbers for our Wronski, it's going to be right here. Alright, so now we're going to use the Wronski. Well, to find u sub 1 prime, it's just going to be Wronski sub 1 over the Wronski, which here's our Wronski sub 1. When we find that, we're going to multiply 0 times cosine of x, which is going to be 0. Sine times tangent is going to be negative sine x over tangent x. I don't know. It should be negative sine x tangent x. What in the world happened right here? So let me just erase it. Anyway, let's just go ahead and write it how it's going to be. It's going to be negative sine squared x over tangent x. Over cosine x. Alright. And then the Wronski is going to be cosine times cosine, which is cosine squared, minus sine times negative sine, which is positive sine squared x. So that's nice. The Wronski is equal to 1. So then we can say our u sub 1 prime is just going to be negative sine squared x over cosine x. Now, I'm going to change the way that this looks and have cosine squared x minus 1, because that's a little bit easier to deal with when we're talking about taking the derivative. And then cosine of x over cosine of x, and this is going to simplify to cosine of x minus secant of x. All right, now we got to take the integral of that to find our u sub 1. So the integral of cosine x minus secant x dx is going to be sine of x minus natural log secant x plus tangent x. Now, if you're having trouble taking the integral, the integral of negative secant x isn't 1, or the integral of secant x isn't something that's commonly known. So that's where you want to use your integration tables of any that you typically find in a calculus book, if you can't do that by hand, which again I advise you to do. And then I can put up the integration tables on, since we don't have a classroom textbook, I could put, kind of all those integration charts, I guess, that you typically find in a calc book or differential equation book. All right, to find u sub 2, we do the Wronski sub 2 divided by the Wronski. So the Wronski sub 2 is just going to be, it's going to be given by cosine of x, negative sine of x, 0 tangent of x, multiply cosine x times tangent x is just sine of x. And then the other part's going to be 0. So then our Wronski sub 2 is sine of x over the Wronski, which we already found to be 1. So that's just going to be sine of x, which is nice. To find u sub 2, we need to take the integral of sine of x, which is negative cosine x. And so we found our particular. Our particular is going to be made up of u sub 1, y sub 1. Let me write that down because you might not know that. Y sub p is going to be u sub 1, y sub 1 plus u sub 2, y sub 2. So our u sub 1 times y sub 1, and then our u sub 2 times y sub 2. And then we clean that up to find our final particular solution. That's going to be, or to find our final solution. So there's going to be our complementary solution. There's going to be our particular solution. Hopefully you've noticed, oh, hey, I have positive cosine x, sine of x minus cosine x, sine x. So that's going to cancel out. And so we're left with our final solution, which is made up of the particular and the complementary. Hopefully you found that wasn't too bad.